In this video, let us find out the relation between free energy and equilibrium constant. The free energy associated with a chemical reaction when it is in equilibrium. Okay, so let us derive the relation between free energy and equilibrium constant. For that, let us consider a general reaction where the reactant A would react with reactant B to give the product L and M. There can be any number of reactants or any number of products. So the reaction is A moles of component A. Reactant A reacts with B moles of reactant B to give L number of moles of the product L and M number of moles of the product M. So this reaction is in equilibrium. So the change in Gibbs free energy delta G for this reaction will be equal to 0, right? Because this reaction is in equilibrium and the free energy change associated with the reaction in equilibrium is 0. So we can write the free energy change for this reaction as the sum of free energies of the product minus sum of free energies of the reactant, that is delta G at constant temperature and pressure, and that can be equated to 0 because this is an equilibrium reaction. Okay, so instead of free energy, we can use the term chemical potential. So delta G for this particular reaction in equilibrium is equal to L into L number of moles, L into chemical potential of product L plus M into chemical potential of product M plus etc. minus those of reactants, right? A into chemical potential of component A, reactant A plus B into chemical potential of the reactant B. Okay, so sum of chemical potentials of product minus sum of chemical potentials of reactant, that is the change in Gibbs free energy, which is equal to 0 because this is an equilibrium reaction. Okay. We know here mu L and mu M are the chemical potentials of the species L and M, and mu A and mu B are the chemical potentials of the species reactants A and B. And we know the chemical potential of a species, say J species or any species, can be related to its activity Aj by the equation mu J is equal to mu 0 J plus RT ln Aj. We have learned this equation when we studied about activity, right? So there is an expression, chemical potential of any component, here J component can be equated as mu 0 J plus RT ln Aj. Let that be equation 2. Where we know what is mu 0 J, it is the chemical potential of the Jth component in its standard state. Okay. Similarly, we can express the chemical potential for Lth and Mth component as mu L is equal to mu 0 L plus RT ln Al, where Al is the activity of component L, and mu M, chemical potential of component M is equal to mu 0 M plus RT ln Am, where Am is the activity of the component M. Okay, now we can substitute these values in the previous equation, right? Previous equation for delta G, we are going to substitute value of mu L and mu M from these equations. So have a look at the previous equation. We have delta G at constant temperature and pressure is equal to small l into mu L plus small m into mu M plus etc. minus small a into mu A plus small b into mu B plus etc. which was equal to 0, right? So let us take L as a constant, let us take L outside. Then we can substitute instead of mu L. We had L mu L, right? So instead of mu L, we can substitute mu 0 L plus RT ln Al. Okay, in equation 1, we are substituting for mu L by these two terms, and L is taken out, so we have mu 0 L plus RT ln Al plus M into, let us substitute for mu M, M into mu 0 M plus RT ln Am plus etc. minus, have a look at equation 1, we are substituting for chemical potential terms of products and reactants. Okay, so here minus A into mu A. Mu A can be substituted as mu 0 A plus RT ln AA plus B into, instead of mu B, we can write mu 0B plus RT ln AB plus etc. And we know since the reaction was in equilibrium, it is equal to 0. So in equation 1, instead of mu L, we substituted this, mu M, we substituted this, mu A, we substituted this, mu B, we substituted this. So we have now the equation in terms of acting. Okay. Now let us collect the mu 0 terms together, mu 0 terms of products and mu 0 terms of reactants together. So we have L into mu 0 L plus M into mu 0 M plus L into RT ln AL. Here we have removed the bracket, so L into RT ln AL plus M into RT ln AM, M into RT ln AM minus A into, we have to collect these mu 0 terms together here, A into mu 0 A plus B into mu 0 B plus A into RT ln AA plus B into RT ln AB, which is equal to 0. We have just opened the brackets and collected mu 0 terms of products and mu 0 terms of reactants together. So now have a look at this equation. We have mu 0 terms together, L into mu 0 L plus M into mu 0 M plus, then we have L RT ln AL plus M RT ln AM, right? So we can take this RT terms out, common RT into ln AL. L into ln AL can be expressed as ln AL raised to L, right? Similarly, M into ln AM can be written as ln AM raised to M. Okay. So since we have ln AL raised to L plus ln AM raised to M, sum of log terms, so we can take it as ln AL raised to L into AM raised to M. Okay. So sum of log terms can be taken as product, right? ln AL raised to L into AM raised to M. RT was taken out already. So these two terms can be combined and can be substituted as RT ln AL raised to L into AM raised to M. Similarly, let this term be there and this term here we can take out RT outside, and A ln AA can be written as ln AA raised to A, small a. Similarly, this term can be written as ln AB raised to small b. And sum of two log terms can be written in this way. So we have this common RT here, ln AA raised to A into AB raised to B. Okay, so we can substitute this term by this term, these two terms by this term. Let us modify our equation. So we have RT into, and have a look here. There is a bracket, okay. So this term is also negative. Okay. So we can write this equation. Just take this RT terms from both sides as constant, and we have ln AL raised to L into AM raised to M minus ln AA raised to A, AB raised to B. So log of these two terms, right? It is expressed as a difference, so we can put them together in this way. RT into ln AL raised to L into AM raised to M divided by, because here it was minus ln term, so here we can write log of AL raised to L into AM raised to M divided by AA raised to A into AB raised to B, which is equal to, we have these two terms, right? Please note there is a correction. This term is negative. Corresponding to this corresponds to product, right? L mu 0 L plus M mu 0 M. These terms correspond to that of the products, and this is negative. And this corresponds to that of reactants, and this is positive. Okay, so there's a sign interchange. Please make corrections in your notes also. And this can be taken as sum of chemical potentials of products. Sum of chemical potentials or sum of free energy of products, and this is minus plus what we have sum of chemical potentials of reactants, or sum of free energy of reactants. This is negative, this is positive. We can take negative sign out, and we have sigma G0 product minus, it was already positive, so minus into minus is positive. So here minus sigma G0 reactant. So minus of sum of free energy of products minus sum of free energy of reactants will be delta G0, right? It is equal to minus delta G0. So we have RT ln AL raised to L into AM raised to M by AA raised to A into A B raised to B is equal to minus delta G0. That is equation 3. And AL corresponds to activity of the component L, and L is the number of moles of component A. Similarly to all other terms. And let us take this RT to right hand side. So we have ln AL raised to L into AM raised to M divided by AA raised to A into AB raised to B is equal to minus delta G0 by RT. That is equation 4. Now we are removing these natural logs. So we have AL raised to L into AM raised to M divided by AA raised to A into AB raised to B is equal to E raised to minus delta G0 by RT. E raised to minus delta G0 by RT. That is equation 5. If the temperature T is kept constant, then delta G0 by RT will be a constant, right? Hence, the left hand side will also be a constant. When temperature is constant, this entire term becomes equal to constant. That means the LHS will be equal to a constant. And that can be equated to Ka, equilibrium constant Ka. So, Ka is equal to AL raised to L into AM raised to M divided by AA raised to A into AB raised to B. That is equation 6. Now, have a look at equation 5 and 6. From 5 and 6, we can equate Ka is equal to E raised to minus delta G0 by RT. If we take the log, ln Ka is equal to minus delta G0 by RT. Okay. So from this we can find out delta G0. Delta G0 is equal to minus RT ln Ka. Delta G0 is equal to minus RT ln Ka. Let that be equation 7, where Ka is called thermodynamic equilibrium constant. Okay, so here we have derived a relation between free energy change and at equilibrium and the thermodynamic equilibrium constant. So we have the expression delta G0 is equal to minus RT ln Ka, and since Ka is in terms of activity, it is applicable to both ideal and non-ideal systems. So this relation of change in Gibbs free energy at equilibrium, which is equal to minus RT ln Ka, this equation, this expression is applicable to both ideal and non-ideal, or ideal and real systems, because Ka is expressed in terms of activity. Okay.